Hey all you guys, gals, and physics pals, welcome to Quantum High, modern physics for high schoolers. Let's get talking. Now, this video is about the Schrödinger Wave Equation. Most of you probably know Schrödinger from his, infamous cat in a box, Schrödinger's cat thought experiment, where if you put a cat into a box, close it, and you have a 50-50 chance of something killing the cat is both dead and alive until you measure it. Well, that's not really what we're going to talk about today. Now, the Schrödinger equation is this big ol' massive thing. Not really going to fully, speak it out because it's long. But the key part is total energy is equal to kinetic energy plus potential energy. That's the basis of the equation because we have to have energy conservation. Now, let's break down the Schrödinger equation just a bit more. So we know we have this total energy term, the kinetic energy term, and the potential energy term. But I want to kind of just ignore that for a minute and just talk about the phi terms, and which is the weird trident-looking piece. We could say that phi, the wave, is equal to the amplitude times the sine of kx minus omega t. That's very generalized. It kind of ignores the cosine part, which should be 0 in places where there's no potential energy. K is the wave number, which is equal to 2 pi over lambda. So with knowing K, you can find the wavelength. And that's a very, very, very key in knowing a lot of stuff about the function, about the particle, which we have defined as a wave. Omega is angular frequency, which is equal to 2 pi times f. So if you know omega, you know f. And if you know f and you know lambda, you know the speed of the wave, you know the speed of the particle, which is very key. So now, knowing the wave function, you know the wavelength, you know the frequency, you know the velocity, which also means you know the momentum, you know the kinetic energy, and you know the total energy, which are all very, very key parts of knowing everything there is to know about the particle through this wave function that we've defined it as. So the Schrödinger equation really is derived from de Broglie's hypothesis that electrons or any piece of matter is a wave. And a lot of it is really just determinant on subatomic particles. I'm technically a wave, but because of my scale, I don't exert any properties of wave-like stuff. Now, the Schrödinger equation also allows for something called quantum tunneling. Now, this is something that's completely mind-boggling, at least to me, but it's if you have a wall of potential energy and you have a particle, it can go through this wall. It has a potential, it has a probability to go through this, which from classical physics is absolutely impossible. But because of the uncertainty principle and because of the probability wave, this particle can technically tunnel through this thing. The majority of the particle will be deflected off of this, but there is a chance because of the probability wave that it can go through, which is just absolutely bamboozling, right? Now, another key part of the Schrödinger equation is probability, and the probability wave function is the integral from negative infinity to infinity of the Schrödinger wave equation squared by dx equals 1, because the particle has to exist, so it has to equal 1. And so then if you define the integral between a finite space, you can determine the probability that the particle will be at that position. The Schrödinger wave equation is also another way that we can quantize energy and quantize the different energy levels within a particle and say what energy level the particle lies on, or especially for electrons. So if that electron operates between a set distance, 0 to L, it has a numerous different wavelengths times L, which can be defined as the wavelength n equals 2L over n. So it's defining that there is a quantized number of wavelengths that the electron can exist at any time. If this wavelength is quantized because it's at a different energy level, then we can say that momentum is quantized because P equals h bar times k, and you can find k from lambda. And you also, because energy is based on momentum, you can find that energy is quantized using this equation here. Now, that's all I really want to say regarding the Schrödinger equation before I get in too much detail and too much science, when this is really just a breakdown and an introduction of the idea. That's all for the video. Thanks for watching. Hope you learned something. And as always, I give you a quantum bye. Get it? Come on, been long enough.